first component will be the boiler. This will be the diagram right here. Okay. Then in here, inside the boiler, there are several tubings that are going back and forth. Okay, somewhat like similar to that of an intestine. Basically, the uh, the what you call this, the tubing would either be it's going to carry the liquid water or the hot gas. No? Depende. Na? So, naman tayo gitawag kung fire tube boiler, nasa tayo gitawag o water tube boiler. So, kung water tube boiler, inside the tube is water. And then the hot gases will be outside and it's going to heat up the water and transform it into steam. And then once the steam is being produced, then it will be delivered towards the steam turbine. The other one is the fire tube boiler. When we say fire tube boiler, the ones that are inside the tubing are the hot gases. Okay, and then outside is the water. Okay, and that's it. Those are the two methods by which the water is being heated up inside the boiler. Okay, and then right here, as we all know, steam generator is a closed vessel that is intended for use in heating water or to generate steam or vapor. Okay, and it is composed of boiler and furnace. The furnace houses the fuel, could either be solid fuel or liquid fuel for that matter, and then of course the air, and the combination of both will lead to the ones called as combustion. And it is usually made up of two drums for the heat transfer of combustion heat to feed water, and then furnace is constructed for the combustion of the fuel. So, let's say this cylindrical diagram represents the boiler. Inside the boiler, we do have the two drums right here. The first drum houses the feed water. The feed water is being delivered by the feed water pump right here. Okay, and of course, the feed water pump or the feed water most likely is pressurized and of high pressure. Right? So, since it is still in liquid state, then it will we will use the H sub F or the saturated fluid enthalpy of the water. Right? Once it is inside the boiler, the combustion chamber is right below, and the fuel is being burned right there, and then the heat will be absorbed by the feed water, and later on the feed water will be transformed into steam. The steam will be deposited somehow on this second container, and it will be held for as long as the temperature is not yet achieved or the pressure is not attained. But the moment the temperature or the pressure requirement is already achieved, then it will be delivered towards the steam turbine. There, it will have its properties such as the enthalpy of the steam and then the mass of the steam. Somewhere here in the combustion chamber, in the furnace, so as what I have said, there will be some fuel for that matter. So whatever fuel we will be using, there will always be heating value in it. And of course, certain mass will be considered. And then there, we are going to burn this one with the use of the air, okay, the pressurized air, and that's it. It is the one that is going to be responsible for the heating process. Okay. Then next slide. This next slide is going to give us the idea on how we are going to design the boiler. And we are going to note also different calculations that are needed. The first one is we are going to compute for the heat generated by the fuel. We call that one as Q sub F. Q sub F is just the product of the mass of the fuel and the heating value of the fuel for that matter. Okay, and the unit of the heat generated by the fuel will be dependent upon on the unit of mass and the mass of the what we call this uh, heating value of the fuel. Okay. The unit for the heating value of the fuel is kilojoules per kilogram, while the mass flow rate of the fuel is expressed in terms of kilogram per hour. So much so that the unit that we can have for the heat generated will be in kilojoules per hour. Okay. So take note that M sub E is the mass of the fuel and Q sub F is the heating value of the fuel. And we have this term as rated boiler. The rated boiler horsepower, or RBH, is the boiler horsepower by which the boiler is going to attend based on the heating surface area. So in that case, we are going to determine the heating surface area, okay, and divide it by 0.91. So kinisi ang kuan, di ba? We all know that when inside the tubing or the water, di ba? So we are going to determine the surface which is being in contact with the water, so that we can determine the amount of heat that is being absorbed based on that surface. So it's quite long, and so it will have a certain value for the heating surface. And then we are going to divide this one by a factor which is 0.91, and the result will be in terms of boiler horsepower or reading. The factor 0.91 is applied when it is a water tube boiler, meaning to say the one that is inside the tubing is water. Now, if the one that is inside the tubing is hot gas, then the factor that we will be using is equivalent to 1.1. Okay? And most likely, the heating surface area are expressed in terms of meter squared surface area. Heating surface area is in meter squared. Aside from the rated boiler horsepower, we do have the ones called as the developed boiler horsepower. The developed boiler horsepower mode, yun is yung actual horsepower that has been developed. And this is based on the energy of the steam that has been produced. So the energy of the steam is the product of the mass of the steam times the difference of the enthalpy of the steam and that of the enthalpy of the feed water. And of course, the unit of this one will be expressed in terms of, this one is kilojoules per kilogram, this one is kilogram per hour. So the unit here is kilojoules per hour, isn't it? So this becomes kilojoules per hour, and 32,322 has a unit of kilojoules per hour per boiler horsepower. So the kilojoules per hour can be cancelled out. Then what is going to prevail is the boiler horsepower. So we should have to take note that the mass should be expressed in kilogram per hour. And we are going to note also that one boiler horsepower is 32,322 kilojoules per hour right there. Then the percent rating. Percent rating is basically the ratio between the developed boiler horsepower to that of the rated boiler horsepower. And of course, you multiply that one by 100. Then we have also such things as ASME evaporation. So ASME evaporation refers the evaporation unit has an acronym which is AAU. And this is equivalent to the actual energy absorbed by the steam. And the unit for this one is expressed in terms of this one, kilojoules per hour. This is kilojoules per hour because mass is kilogram per hour, and this one, the enthalpy change is kilojoules per kilogram. Then we have also the ones who called as the factor of evaporation, that is FE. The factor of evaporation is equal to the ratio of the actual energy in kilojoules per kilogram achieved by the steam and divided by the amount of heat that is needed in order to vaporize the water okay, per unit kanang kuan. The unit of this one is kilojoules per kilogram. Yan, sa babaw sa kilojoules per kilogram. So, mag-cancel ang unit. So, in that case, the factor of evaporation doesn't have any unit at all. Okay? So, 2,257 is the latent heat of vaporization. With regards to boiler efficiency, the boiler efficiency is equivalent to the output over the input. Basically, the input is the heat that is being absorbed by steam and divided by the heat that is being developed by burning the fuel. That's it. Next, we have the net boiler efficiency. Yes, we do have a boiler efficiency, but there is also this net boiler efficiency. And the difference between the two is that we try to include the auxiliaries here in the competition. Okay? So, why? Because the auxiliaries are going to need energy. And the one that is going to provide this one is the steam. So much so that the heat that is being given off to the auxiliaries are a portion of the heat coming from the actual generated heat or absorbed heat by the steam. So much so that we are going to subtract it from there. Okay? Just like that. You might be wondering as to what are those auxiliaries. These auxiliaries, example of this one is the economizer. Okay? So, economizer can be considered as an auxiliary. The heat is coming from here. Okay? And then we do have also the actual specific evaporation or ASE. This one is basically the ratio of the mass of the steam to that of the mass of the fuel. We have also the ones who called as the equivalent evaporation or EE. The equivalent evaporation is basically the product of the mass of the steam times the factor of evaporation. Just like that. Okay, and then for the equivalent specific evaporation or ESE, the formula is basically the ratio of the mass of the steam to that of the mass of the fuel, multiply it by the factor of evaporation. Then here, we are going to have the sample problem. It seems ang akong kanang kuan dili ta magkakandak o computation right now. As what I have said, what had happened is that I wasn't able to subscribe to what you call this class point. It requires a payment for that one so that we can have it. We can use the subscription. Unfortunately, wala mo gana ang kanang kuan. 7-Eleven kanina. Nakupugsa. Maybe perhaps in the next presentation na lang siguro nato, guys. For now, our first question is a steam boiler on a test generates 885,000 pounds of steam. So this is the mass of the steam in 4 hours period. So in that case, in order to for us to compute for the mass of what we call this the steam, so we are going to divide this value by 4 hours so that we can have pounds per hour, isn't it? Then the average steam pressure is 400 psi. Okay, and the average steam temperature is 700 degrees Fahrenheit. And the average temperature of the feed water supply to the boiler is 280. So, mauni siya sa itong boiler. Ako lang ipakita siguro ang diagram no para atong masabtan given data. Oh, sorry. So, mauni siya guys no. The mass flow rate right here. The mass flow rate is or the mass only is 885,000 pounds, and then the time is 4 hours, just like that there. Then the steam condition is dependent upon on the pressure, as given in the problem 400 psia and 700 degrees Fahrenheit. So in here, we do not have the value for the enthalpy of the steam, isn't it? So in that case, this one, during the time when this problem was given, it is supplied with a table for that, or a steam table. So that's it. When you're going to refer to the steam table at this pressure and that temperature, the enthalpy is 1362.7 BTU per pound. Okay, and then somewhere sa feed water, the temperature there is we have 280 as given in the problem. So at 280 Fahrenheit, so you're going to look for the temperature and then 280, and there you are going to determine the H sub F, saturated fluid, for this enthalpy. The value is 249.1 BTU per pound. Okay? And then what else? There was this mention of the fuel. It has its heating value, which is 13,850. So it's right here. What is asked in the problem? Find the average amount of the coal burned in short ton per hour. So the mass of the fuel that is being asked. Okay. So if you're going to take a look at it, okay, what will be the first thing that we are going to do? Remember, there was this mention of the boiler efficiency. So in this case, we need to use the formula for the boiler efficiency. That is, boiler efficiency is output over input. The output is M sub S times H sub S minus H sub F, all over mass of the fuel times the heating value of the fuel. So it's like this, guys. This is the formula. So since it is the mass of the fuel that is being asked, so I try to swap the position of the mass of the fuel and that of the boiler efficiency. And with that, we are now free to substitute the value. So we must have to express the mass of the steam in terms of pound per hour. So that's why we try to divide 885,000 pounds per over 4, then divide it by the enthalpy. Okay, H sub 2, that is H sub S, right? And then H sub 1. Okay, the H sub 1 right here is the H sub S. So basically, this is H sub S times H sub S. Okay, and divided by the boiler efficiency, heating value. And once we are going to compute this one, the resulting unit will turn out to be in terms of pounds per hour. But we do have a problem. The unit requirement is short tons. So how shall we do it? So when you are going to compute that one, this is the resulting unit, pound per hour. And to convert that one to short ton, take note on this one, guys, that 1 short ton is equivalent to 2,000 pounds. Okay, 1 short ton is 2,200. Okay, or if it is not short ton, the normal conversion is 2,200 pounds. 2,200 pounds. So with that, the pound can be cancelled out. Then the unit is short ton per hour. And there you go. So we'll try to check if indeed the computation is correct. So we'll try to see right here, guys. So in here we have the fraction of 885,000 divided by 4. Multiply that one to the difference of 1362.7. Oops, 0.7 minus 249.1, and then close parentheses, bring it down, is 0.825 multiplied to 13,850. And with that, proceed with the computation. The answer is 21,262.98, round off. round it off to whole number of 21,600, 563. So just right there. And then we're going to get the answer. We're going to divide that one by 2,000 pounds. And the resulting value is 10.78. Therefore, the answer is 10.78 and it's correct. And the closest possible answer is 10.75. So in that case, we will be selecting the closest possible answer. Right? Okay, and that is letter B. I guess this one is clear, guys. Okay. We are going to proceed